In this presentation, we're going to look at comparing the timings between different search algorithms. In previous presentations, discussions, we've looked at a linear search and a binary search, and today we want to compare them, not just on their complexity as we've already seen, but on the actual timing of them. So let's start out with some basic includes. We want to do some output, and we might need a vector to store our list, and then use chrono to do some timing. And then let's grab our search functions. So we have two searches. The first one is a simple linear search. And in the linear search, we just have an index that goes from 0 to the size of the list. And if we find a match with the target value, we set the return index to that and break out of that loop and return it. We initialize the found index to -1, which would indicate that it's an invalid index, so it must not have been found in the list if we get that value back. We pass in the list as a constant reference, so we pass the list in as a reference for performance reasons so that we don't make a copy of the list. And since a search function won't change the value of the list, we pass it in as a constant. Of course, the return type is an integer. It's an appropriate type for an index. The binary search has the same signature. We pass in the list as a constant reference, we passed in the target value, we return an integer index, but it works differently, as you recall. We set up 3 indices into the list, one at the low end, one at the high end, and one in the middle. And for a binary search, we have to have the list sorted. So we ask the question if the target value is at the middle location of the list. And if it's not, then is it in the lower half or is it in the upper half? If it's in the lower half, we move high to mid -1. If it's in the upper half, we move low to mid +1 and recalculate the middle of the list. So we've divided the list in half, eliminated half of the possibilities on each iteration of the binary search. Our terminating condition for the binary search is when those low and high indices cross, when low becomes greater than high. Other than that, other than the code in between the signature and the return is really the same. It's just how it's implemented. So what we'd like to do is to try to test these out in terms of timing. When we do comparisons of timing, we want to be careful of what's in between the timing that we're doing. In between the getting the start time and getting the end time, we want to make sure we don't do any input and output operations, which are notoriously slow. So printing things out like with a cout, you try not to do that inside a timing. So for that reason, we're going to do something a little bit different. We're going to store the results of a linear search in a list. So what we're going to do is to create something that's a little bit different, something we haven't seen yet. We're going to store a vector of pairs of values. So the linear search results is going to be a list or a vector of 2 integers, a pair of integers at each location. And we can access the values in the pair using the names first and second. That's what they call them. So the STL library has this thing called a pair, which stores pairs of values. And the first value in the pair is the target value that we're going to be searching for, and the second value in the pair is the search result. And if we initialize a random number generator to the same seed, then we should get a same list of random numbers, and we should get the same results for the linear search and the binary search. They should either not find it in the list or find it at a particular location, but the results should be the same. So now we're going to create some random numbers and put them in our list. So I've defined the list size here to be 100, and I go from 0 to the list size and create a random number between 0 and 100. So the rand function returns a value between 0 and 32,000 some. So we'll use the mod operator to create a random value between 0 and 100 and put that in the list. And here I'm using a feature of the vector class where you can set the size of the list in the constructor. And so I'm setting the size to be 100, so I don't have to use the pushback. I can just access any one of those 100 locations as we would in an array. And the other thing we need to do for the binary search is we have to sort this list. There's no guarantee that this list is going to be sorted. And so C++ has a sort function. In algorithm, there is a sort function. And to use the sort function, you pass in an iterator to the beginning of the list, an iterator to the end of the list, and a comparison function. So this is kind of interesting. You're passing in a function. It turns out a function name is a pointer. Instead of being a pointer to code, a pointer to data, it's a pointer to code, a pointer to an area in code. So we pass in the iterator to the beginning of the list, the end of the list, and then some comparison function. Well, it's pretty easy to write a comparison function to sort a list of integers. All you have to do is ask if it's greater than or less than, if it's greater than or less than, depending on whether you want ascending or descending order. So once we've done that, then we can just write sort, and you have to include the algorithm header file. And we say sort list.begin, list.end, and our sort compare function. And that should take care of sorting the list. Let me just run a quick compile on this. It's saying that sort isn't found. We forgot to include algorithm. Alright, so now we're ready to run our timings and compare the search results. But before we do that, we're going to set up our search results lists for random values to look for. So remember, our search result list for binary and linear search are a list of pairs of values. The first one is the target value we're going to search for, so that's going to be a random value. And then the second one is the search result, the index where it was found. We won't know the second one until we actually do the first, until we do the search, but we can set up the random values ahead of time. We don't want to time creating a list of random values. So we can resize the linear search results to say we want to search for 10,000 values. And we want to search for 10,000 random values in the same range as the random values that we added to the list. So we're searching for 10,000 values between the range of 0 and 100. And we're putting that random number in the constructor of a pair of two integers. So the first thing is going to be this random number. The second one, the search result, we don't know yet, so I'm just going to put a -1 there. We'll fill that in later. Let's do the same thing for the binary search. So both the linear search and the binary search has got a set of random numbers in there. And to make it really fair, it's probably best if we use the same random numbers. That might be a little more of a true comparison there. So now that we have our search results set up, at least the target values set up, we're ready to do some timing and try to compare times. So let's start off with the linear search. We have the begin time for the linear and the end time for the linear search, and the duration for the linear search. So for each one of these random target values in the linear search results, we're going to perform the linear search on the list looking for the first value of that pair. And remember, the first value of that pair is the random number that we're looking for. The result that we get from the linear search will be the index of where that random number was found, or a -1 if it was not found, and we're going to put that in the second value of that pair. So I wonder how long this will take us if we run this. So I've got an error message here that says vector subscript out of range. So I've got a bug here already. So let's see if we can figure this out. It says press retry to debug the application. And we end up in the vector code, which is part of the STL library. We don't want to change that. We want to find out what we did wrong in our program. So I'm going to go here in the debug, this output area, to the function call stack. And I'm going to back up So main called vector pair allocator or something. I'm going to back up to main line 76, just double click on it, and this is where it caused a problem. And the problem here is that we're trying to access binary search results sub I, but binary search results wasn't sized. And so the linear search results was okay, we resized it. We also need to resize the binary search results. Alright, so let's try that again. Okay, so for a list size of 100 and 10,000 searches of a linear search in a list size of 100, it took us 5/100ths of a second. Alright, well, let's compare that with a binary search. We know that the list is sorted, so let's compare that with a binary search. I'm going to do the same thing as I did right here, except I'm going to change this to begin time binary. And end time binary. And duration binary. You have to be careful when you do this copy and paste that you change everything. And in here, the results, the search results, are the binary search results. And maybe most importantly, we want to make sure we do the binary search instead of the linear search. So I have a begin time binary, an end time binary, a duration binary, which is end time binary minus begin time binary, and duration binary count on the output, and I want to label that as binary search time. In the loop, I go from 0 to binary search results, and remember, binary search results is a list of pairs of integers. The first thing in the pair is the target value that I'm looking for. I'm looking for it in the list while doing a binary search. The result of that search is going to be the index where it's found, or a -1 if it's not found, and I want to store that as the second value of the pair in the binary search results. So let's take a look and see if that runs at all. And you can see that the linear search time is 5/100ths of a second, but the binary search time is 7/1000ths of a second, so it's substantially faster. Are we getting the same results? This is something we should compare. Since we're looking for the same random values in the same list, the linear search is looking in list, the binary search is also looking in list, and these random values are the same, we should get the same search results. So let's print out not all 10,000 of them, but let's print out the first 20 or so and verify, see if we're getting the same results. So I have a loop that goes from 0 to 20, and the target value should be the same. Linear, no, it should be linear. And then binary. So we're going to print out the linear search result first, which is the target value we're looking for, and the binary search result first, which is the target value we're looking for, and those should be the same because we put in the same random value here. And it should be a random value between 0 and the list size of 100. And then we're printing out the linear search results second and the binary search results second, which should be the location where it's found, either an index of 0 to list size, 0 to 99, or -1 if it's not found. So let's see what happens. We run that. And so unfortunately, this didn't print out very neatly, so it's maybe difficult to read. So let me put in an extra indel here, I guess. Put each result on separate lines. So okay, so on our output here, I probably should have put an extra space, but the linear search target value is 33, binary target value 33. That makes sense. Linear search result 32, binary search result 32. Looking for 15 and 15, and it wasn't found, so I got a -1 and a -1. And what I'm doing is verifying that the results I'm getting for the binary search are the same as for the linear search. And it should be the case that they are the same because I'm looking for the same random value in the same list. It's just one method is faster than the other. So the results look like they match up like we expect. So I'll comment this out, and what I'd like to do is to perform this time for different sizes of lists. So as you recall, we talked about the complexity of a linear search being linear or order n in the Big O notation. We also talked about that a binary search, because it's dividing the list roughly in half each time, has a logarithmic complexity or a log n in Big O notation. Is there any way we could verify that? What I'll do is create another list of list sizes. So here I set the list size to 100. What I'll do is to create a vector of list sizes. So we'll run this experiment for a size of 100, a size of 1,000, a size of 5,000, a size of 10,000, and a size of 30. Let's do 20,000 and then 30,000. Because and the reason I chose this limit is because I know that the random number generator just gives us values in the range of 0 to 32,000 something. So I don't want my list size to be larger than the number of random values that I have to fill it. So and then now, instead of list size being 0 to 100, I'm going to use a range-based for loop for list size in my vector of list sizes. And I'll be printing out these different times. And it might be helpful for my experiment to store the different times. I want to store the linear search time and I want to store the binary search time and then print them all out side by side as a comparison. So again, I can create another vector of times, and so I'm going to create another vector of pair, and these are the search time results. And so the first one in the pair is going to be the linear search time, and the second one in the pair is going to be the binary search time. So when I finish doing both searches, I can push back a pair of doubles, and it's going to be the linear time and the binary time. So I'm creating a constructor, using the constructor for a pair of two doubles, and I'm passing in the time that I got for the linear search for this particular run of list sizes, and I'm comparing, and then I'm pushing back the duration for the binary search for that particular list size. And it looks like I'm missing a closing brace for the, oh, there it is. So when I'm finished with this loop, that collects all this search time data, then I can print out the results. And the search time results should be the same size as the list sizes list. So I'm searching in 100, 1,000, 5,000, 10,000, 20,000, 30,000. I'm searching in lists of different sizes. And for each one, I'm searching for 10,000 different values. And so when we're done, we should be able to print out the size of the list and the times that we got for the linear search and the time that we got for the binary search for each list size. And this might take a minute or two to run. I'm not sure how slow it'll be for 10,000 searches in a list of 30,000, but let's get it started and see what happens. And then not only are we timing the searches, but we also have to wait for the list to be sorted. We have to sort 20,000 and 30,000, so this might take a second or two to run. We can see that we're up to 9 seconds on the linear search. And let's see, what was it? It was, oh, we're done, good. So it didn't take quite that long, but so if when the list size was 100, the linear search was 0.05 and then 0.007. When it was 1,000, it went up to almost 0.5 and 0.000. That was, wow, that was really fast. That's, sorry, 0.008, yeah. And then when we got up to 5,000, it was almost 2.5 seconds and 0.01, 10,000. You can see the results here. What I want to do now is to graph these and see if they follow what we expect based on what we know of the complexity of a linear search and a binary search. So let me just mark this output and copy it, and I'm going to use Visual Studio's nice selection tool where I can get this data in columns. So the search time for the linear search were these values, and the search time for the binary search were these values. And now I have a spreadsheet here in Google Sheets that has some graphs set up, and I can take the linear search data and put it in the linear search column, and we need to fill in the values of the list sizes, and it went from 10,000 to 20,000 to 30,000. And then fill in the data for the binary search, and then we'll modify the ranges on the graph. So let's make the top one be the linear search, and so its data range for the x-axis is A4 to A9. That makes sense. And then for the series that we want to plot is B4 to B9. That makes sense. So the top one is for the linear search, and then let's make the bottom one for the binary search. And its range is A4 to B9. And we want to change this so that it's C4 to C9. And what you can see is that for the linear search we have roughly a straight line, and for the binary search we have this curve here that's, if you look up, if you do a search for logarithmic plot, you'll see curves something like this that are similar to what we see in this plot of our data. So in this presentation we've seen the difference in performance between the linear search and the binary search, and not just in terms of specific times but also in trends of how those times change based on different list sizes and how they compare to the algorithmic complexity that we know of those particular algorithms. Let me know if you have any questions about this.